In section 6.6, we're working with absolute value integrals. And sometimes we have to calculate the absolute value the absolute value of our integrand. We have to calculate that integral by hand. So if we just look at this example, I'm not going to read all of the text on page 93. I'm just going to go through the examples. If you look at the top, though, where we have this quadratic function x squared minus 4x. If I want to integrate from 0 to 4, so I'm just looking at this area here from 0 to 4, I'm expecting to get a negative number when I do this. So x squared minus 4x dx. And I know that the graph x squared minus 4x is always negative there, because I can see it with my eyes. That won't always, we could do it algebraically, but I'm just going to go with the graph on this one. All right, so if I integrate that, I know I'm going to find the antiderivative of x squared, so 1/3 x cubed minus 2x squared, and I'm going to evaluate that from 0 to 4. So I'm going to plug in my upper limit first. That's 4 cubed over 3. That becomes what, 64 thirds, minus 4 squared times 2, so that's what, 16 times 2 minus 32, and then all of that minus 0 cubed over 3 minus 2 times 0 squared. So we get 64 thirds minus 32, which is like negative 10 and 2/3. I'm going to say negative 10.667. Okay, so it stands to reason that if we take the absolute value of that integrand, we should expect to get a positive number. And when we graph the absolute value of any function, it just reflects the part of the function that's below the x-axis to be above the x-axis. So like going out to the side, if I think about y equals x, like the easiest thing I can think of, right? We know the graph of y equals x is linear and it has a slope of positive 1. Well, if we instead graph the absolute value of y equals the absolute value of x, well, the part that's above the x-axis stays, but the part that's below gets reflected up. So the same is going to happen for any function if we graph its absolute value. So all that to say that when we integrate, and we're integrating the absolute value of x squared minus 4x, that we're going to change the sign. So because we know that this graph is always below the x-axis from 0 to 4, that means the value of this integrand is just going to be negative 1 times the definite integral from 0 to 4 of x squared minus 4x. So we get a positive 10.667. All right, I'm not going to read through this entire example, but we're going to go through this process algebraically, and it's going to require, it's a lot of work. I'm not going to lie, it's a lot of work. But again, the purpose of doing this without the calculator is that sometimes we need to. So let's just look at these 3 examples on page 94. And so if I'm going to integrate the absolute value of x cubed minus 4x from 0 to 3, I first really need to know where x cubed minus 4x is positive and where it is negative. So if I want to know where it's positive and negative, I need to set it equal to 0 and solve. So I'm going to say 0 equals x cubed minus 4x. I'm just working with the integrand. I will always, 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 always factor. I will never, ever, ever divide both sides by x. And when I get a difference of squares, it's my preference to factor that as well, so as to not forget the positive and the negative solution. All right, setting each of these factors equal to 0, we get our 3 solutions. and we need to put those on a number line. So if we want to think of this in steps, step 1 is find the zeros of the integrand. So the function that is in our integral. Step 2, I would say, is to make a number line. So on my number line, I'm just going to put those 3 numbers in the correct order. And we're not working with the derivative. I know it's similar to what we do with relative maxes and mins. I just want to know where this function is positive and where it's negative. So let's say I plug in a -10, and I'm not working with the absolute value right now. We're just working with the function x cubed minus, x cubed minus 4x. Timer tells me my crock pot is done. Okay, if I plug in, like, say, a -3 or a -10, cubing that, actually, let's use 3 since it's a smaller number. -3 cubed is -27 minus 4 times -3, so plus 12. We are negative out here. Let's say I plug in a -1. -1 cubed minus 4 times -1 is 1 plus 4. So we are, -1 plus 4, but we're in the positive. And then if I plug in a positive 1, so 1 minus 4, we're back in the negative. And if I plug in a number greater than 2, so like a 3, we've got, 27 minus 12, so we're in the positive. So I'm just testing the function on the number line. Okay, so if we want to integrate from 0 to 3, we need to take into account that where the function is negative, so from 0 to 2, we're going to need to integrate that, and then we're going to need to multiply that by -1. So just like up here, if you've got a negative area under the graph, we're just going to multiply it by -1 to get the positive area. And then the place where the function is already positive, so from 2 to 3, because we're integrating this from 0 to 3, I don't need to change that. So after we make our number line and we reason through it, I'm going to rewrite the integral. So rewrite integral, and this will allow us to get rid of the absolute value because we can't integrate an absolute value function. And if we remember, the absolute value graph itself has a corner, so it's not differentiable everywhere. Okay, so as I rewrite this, our original integral from 0 to 3, the absolute value of x cubed minus 4x dx. I know that that graph is beneath the curve from 0 to 2. So I need to split this up, and I need to say that from 0 to 2, I'm going to integrate x cubed minus 4x dx. But because that gives me a negative area, I'm going to multiply this by a -1. And that's going to allow me to drop those absolute value bars. And then I'm going to add to it the rest. So, not from 0 to 3, from 2 to 3. And since our graph of our function is positive there, or rather our function is positive there, I do not need the -1. Okay, so when we find our integrand, our antiderivative, our antiderivative is going to be what? Like 1/4 x to the 4th minus 2x squared. And when we integrate that from 0 to 2, we're going to multiply that by a -1. So if I do that out to the side, I have 2 to the 4th power. So let's see, 2, 4, 8, 16. 16 over 4 is just 4. Minus 2 times 2 squared. So 4 times 2 is 8. And then I'm going to plug in my 0 and subtract that, but I just get 0. So, oh yeah, and you know what? I should put my -1 out here in front. So I get 4 minus 8 minus 0, so negative 4, times that negative 1, which is 4. Okay, when we do the other part of it, I'm just doing these separately because there's so much going on here. When we integrate from 2 to 3, actually, I'm just going to write it out separately. So we already have our antiderivative, so we only have to find that once. From 2 to 3, when I plug in the 3, let's see, 3 to the 4th is that 81? Yeah, 9 times 9. So we get 81 over 4 minus 2 times 3 squared, so minus 18. And then minus, and then we got to plug the 2 in. Let's see. Well, we already plugged the 2 in earlier, right? Like this 4 minus 8 was what we got when we plugged the 2 in. So that would be a negative 4. So it's like minus negative 4. All right. We can totally do this by hand. I'm just feeling a little bit lazy. So I'm going to pull up my calculator. I don't think this is something that would be outrageous for us to do by hand, but all right, so 81 fourths. And then we are, what, subtracting 18 and adding 4, minus 18 plus 4. So we get 6 and a fourth, or 6.25. Okay, so going back up here to our, where we rewrote the integral, we get 4 for the first integral. We get 6.25 for the second. So when we add those together, we should get 10.25. Now, the purpose of this section is to do this without the calculator, but it's a great tool to use to practice, to check and see if we did this correctly. And it also helps you practice doing antiderivatives in the calculator. So if I go to Math 9, and I haven't stored this, I'm just going to type this in. So we said from 0 to 3, and then when I go into my integrand, to get to the absolute value, I need to go to Math, go over to Number, Abs, and then var. Oh no, never mind. I forgot I didn't put it in Y. So never mind about the vars unless you put it in Y1. I'm just going to type it in since I didn't do that. So x cubed. Sorry, I'm trying to make this video shorter because the last one was so long, but oh no, but I'm making mistakes. I forgot to arrow out of my exponent. X cubed minus 4x, and then that gets a dx. All right, so it's funny because it actually gives us a number that's not totally correct. Our number is correct, and it just has to do with how the calculator runs this operation. So 10.25 is the correct answer. All right, let's try the next one. Again, the same process. We said the first thing, we want to find the zeros of the integrand. So I want to set my integrand equal to 0. And there's nothing to factor here. We always check for factoring first, but there's nothing to factor. So instead I could add 1. And then if I need to undo an exponential, I use the inverse function. So I'm going to log both sides with the same base. So log base e, or natural log. And when we do that on the left, we get x minus 2, and the natural log of 1 is 0. And then we could add 2 to both sides, so we get x equals 2. All right, that's going to make our number line step a little bit easier because we only have one thing to consider, and it's the number 2. So when we consider this function, I'm just going to call it f. If I plug in a number to the left of 2, let's just say I plug in, let's say I plug in 1. E to the power of 1 minus 2, all of that minus 1, is e to the negative 1, or 1 over e minus 1. And 1 over e, like that's 1 over 2.7 and some change, that's going to be a negative number. And then if I plug in, say, a 3, I get a positive number. E minus 1 is positive because e is about 2.7. So I know that this 2 is where I need to break up my limits. So from negative 2 to 2 and then 2 to 3. And I need to set the first part. I need to integrate, and then I need to multiply by negative 1 because I'm going to get a negative area if I just integrate the first part. Okay, so let's see. If we integrate this, I'm going to rewrite this as from negative 2 to 2. Since that's the part that's negative, I'm going to multiply by negative 1. And we're going to integrate e to the x minus 2 minus 1 dx. And then we're going to add to that from 2 to 3, e to the x minus 2 minus 1 dx. So if you want to, we could do a little u sub. I'm not sure. You might be able to do this one in your head. I'm just going to do it out to the side. I'm just going to find the antiderivative as a function. So if we need to integrate this by hand, I could do a u sub for x minus 2. So if u is x minus 2, then du is just 1 dx. So if I did this with a u sub, this would be e to the u. I would keep the minus 1. This would become du. And then we could take the antiderivative, which would be e to the u minus 1u. And, plus c, because I'm doing this without limits. And then lastly, we could plug in or resubstitute our x minus 2. So this becomes e to the x minus 2 minus, needs to be in parentheses, x minus 2, all of that plus c. Okay, so that is our antiderivative. And we know we don't really need the plus c for the purpose of our integral. All right, so we're going to use that antiderivative. I'm going to multiply by a negative 1 for the first part. So e to the x minus 2. I guess we could have just transformed our limits to be values of u. And then this minus x minus 2, that becomes like minus x plus 2 if we distribute that negative. So minus x plus 2 from negative 2 to 2. And then we're going to add to that e to the x minus 2 minus x plus 2 from 2 to 3. And I know I just don't have a lot of room on here. All right, so if I plug in my limits, I have a negative 1 times e to the 2 minus 2. So that's e to the 0. Minus 2 plus 2 will cancel out. So I'm going to get e to the 0 for plugging in my upper limit. I guess I could write this out if it's helpful to see it. And then I'm going to subtract from that the negative 2 plugged in. So e to the negative 2 minus 2 is e to the negative 4. Minus negative 2 is a plus 2 plus 2. All right, so this alone becomes negative 1 times e to the 0 is 1. These 2's cancel out. And then if I distribute that subtraction, minus e to the negative 4, or 1 over e to the 4th, minus 4. So I get, let's see, 1 minus 4 is negative 3. So this is negative 1. I'm just writing in no man's land out here. Times negative 3 minus 1 over e to the 4th. And then that is, if I distribute the negative 1, 3 plus 1 over e to the 4th. Or if I wanted common denominators, I could say 3 e to the 4th plus 1 over e to the 4th. All right, that's just my integral from negative 2 to 2. Then I also need to integrate from 2 to 3. But when I integrated from or when I plugged in my 2, when I plugged in my upper limit, this is what I got. So I already know that piece. So that should hopefully save us some time. So now when we integrate from 2 to 3, we've already got our antiderivative. When I plug in the 3, e to the 3 minus 2 is just e to the first power minus 3 plus 2. And then I'm going to subtract from that what I get when I plug in the 2, which is just the number 1, like we got it. And then we simplified it. All right, so that's e minus 3 plus 2, which is minus 1, minus another 1. So e minus 2. So we're adding this and e minus 2. This is like the messiest work ever. So this is not a good example. This is not an exemplar, but it's fine. These problems are such a pain. All right, so the value of this is going to be e minus 2 plus, I'm writing it in opposite order, 3 e to the 4th plus 1, all of that over e to the 4th. All right, I'm going to stop there. If we wanted to get common denominators, we could. So what I want you to do is pause the video, plug that into your calculator, and see if we got the right answer. All right, I plugged that last example into the calculator, and then I also plugged our answer in because it's not going to give it to us in terms of E, and both those answers are the same. I'll be honest, I started to second guess myself there a little bit. All right, let's try this last one. This should probably be the easiest one, so we got this. On the last example, I'm going to follow the steps. I'm just going to do this. Sorry. Hope you're not running out of room in your spiral. We said we want to find the zeros of the integrand. Well, that should be easy. Where x minus 3 equals 0 is where x equals 3. Then we said we want to put that on a number line. To the left, if I put in like a 1, 1 minus 3 is negative. To the right, if I plug in like a 5, 5 minus 3 is positive. So we're going to break this up from -1 to 3. We know that's where our function's negative. So I'm going to multiply by -1, and I'm going to integrate x minus 3. And then from 3 to 4, our function's already positive, so we don't need that -1. All right, this one should be much easier. Find the antiderivative. So let's see, that is 1/2 x squared minus 3x. And then when we evaluate that from -1 to 3, we need that -1 out in front. So let's see, 3 squared over 2, so 9/2, minus 9. Oh yeah, and let me put this -1 out in front so I don't forget. That's what we get when we plug in the 3. Minus, when we plug in the -1, 1/2 plus 3. All right, so 9/2 minus 9 is like, what, -9/2? 1/2 plus 3 is like, what, 7/2? So yeah, 6. Oh man, I'm doing math in my head. You never know if it's gonna be right or not. Probably not. Okay, so let's see. -9/2 minus 7/2. That would be -16/2 or 8/2. Or 8, which times -1 should be a positive 8. All right, we'll see. I hope that's right. So that's the first part. The last part from 3 to 4. So remember, we already know what we get when we plug in the 3. When we plugged in the 3, that was our -9/2. So now we've got to plug in that 4. So 1/2 x squared minus 3x. Evaluate that from 3 to 4. All right, we have 4 squared, 16 over 2, which is 8, minus 3 times 4, minus what we got when we plugged in the 3, -9/2. So -4 plus 9/2, which is -8/2 plus 9/2, which is 1/2. All right, so hopefully our answer, when we add those together, is 8 1/2, or let's just say 8.5. Let's check it in the calculator real fast. All right, I paused the video and I plugged it in. And so you might notice when you do this in the calculator, you get 8.4999 instead of 8.5. I want to be really clear. The exact correct answer is 8.5 exactly. So if you are wondering why the calculator can't do it, and you might need to research TI a little bit, but I believe that is because the calculator does a ton of tiny Riemann sums. So the calculator is actually doing Riemann sums when it calculates an integral. It does it much better and with a very tiny delta x, but that is why we are sometimes off just a little bit. So we are exactly correct when we get 8 1/2, and the calculator is just not as smart as we are sometimes. All right, that's it for this section.